Okay, so we're going to talk first of all about reliability. And before we get into reliability, I want to spend a bit of time explaining reliability because this is a topic that a lot of people maybe don't understand to the level that is needed for to be able to really evaluate what does it mean when someone says 3 nines or 5 9 reliability. So first of all, I want to talk about the reliability of a single unit. And though we're talking about power generation, this could be in reflection of any sort of product. So single unit reliability is measured by the total time that it's available, so total time minus the downtime over the total time. So for this case, if we assume that this engine is going to require approximately 500 hours of service or downtime per year, we have 8760, which is the number of hours in a year. I was going to say an average year. Average years have the same amount. I guess you have a leap year. Anyways, 8760 minus 500 hours over the total number of hours, the reliability of a single unit, so the single unit reliability is 94%. Pretty straightforward. That calculation can be used for pretty much any single unit reliability calculation. Where this gets tremendously more complicated, and for those of you that are terrified by equations, I purposely made this equation look scary. I'm kidding. A total system reliability is a statistical calculation that requires a much more complex approach to calculating it. And what I'm going to do is, for the sake of just making sure we're all on the same page here, I'm going to really quickly do some explanation on how this works. So a total system reliability, our total, is ultimately a function, of the reliability of a single unit. This is what's very important to know, is that the higher the reliability, obviously, the higher the total. But what you're going to see is that as we sum the number of iterations of additional equipment that meets the requirement, as you add more equipment, this process is iterated over and over, and you get to a higher number. Let me explain that. Ignore generators. Let's just assume we have a situation where you have some fictitious 10 units installed of something. So we're going to need to calculate what is the percentage of time, or what's the system reliability where 8 units are available, where the R single is 90%. So 8 units are needed. We have 10 units installed. Single unit reliability is 90. What is the total system reliability? And so how this is done is we need to calculate the likelihood that exactly 8 units are running, because we're going to iterate this process between 8 and 10. So we exactly 8, exactly 9, and exactly 10. And how we calculate exactly 8 is we are going to take the binomial coefficient, so the number of ways to choose K working in a total number of units. So there are 45 combinations, where exactly 8 units can run. We're going to multiply that by the single unit reliability to the power of K, which is, in this scenario, it's 8, multiplied by 1 minus its reliability to the power of 10 minus 2. So the reliability, or the likelihood of 8 units running exactly 8, is 19.37%. Exactly 9, I'm not going to go through this again, is 38.74%. Exactly 10 is 34.87%. So when you aggregate and you add all of that up, what we're achieving here is a total reliability where single reliability is 90%, but because we now have 10 units require 8, the total reliability is 92.98%. I know I'm getting into the details here. There's a really important reason why we're doing this. Is because when we talk about reliability, just because I have 100 units for 250 megawatts, the statistical system reliability is 0, which isn't very good. Albeit that makes a lot of sense, because if you only have 100 units and you need 250 megawatts consistently, we know that you're going to need to do an oil change or spark plug replacement or some sort of service work on each of these engines throughout the year. So it makes sense that one of these units is going to be down at one time, meaning that our reliability to provide 250 megawatts is absolutely zero. That's why we are able to increase our reliability by adding additional units. And what you'll note very quickly is that the total increases very quickly. So by adding 1 unit, our system reliability increases to 1.4, but by going up to 10 units, we're up to 93.4. And then by adding another 5, so 115 units, we reach a system total of 99.9% reliability. What I want to show here is the power of redundant units and the power of having them paralleled to be able to meet that reliability requirement. I hope that makes sense. If you want to go through this in more detail, I'd love to find a time to meet with you virtually or individually or as a team, and we can go through the math here. So I want to compare, now that we understand the difference between single unit reliability and total system reliability, let's get into how large turbines, 50 megawatt turbines, medium speed engines, and high speed engines work together to achieve that 99.9% reliability. So to meet the base load of 250 megawatts, obviously we're going to need 5 of these units. We're not considering any sort of elevation or temperature derate. We're assuming that we're able to produce that full 50 megawatts. 13 20 megawatt medium speed, and I know this sounds like a lot, but 100 2.5 megawatt recips to meet that base load. And what we're seeing here is that right off the bat, the base reliability, so having the base number of units, we see approximately an 80 to 90% reliability on the turbine solution, somewhere between 40 and 50% reliability on the medium speed, and as I already mentioned, 0% reliability on the high speed Rolls-Royce solution or high speed engine solution. However, as we add additional units, you start to see this reliability increase. So as we add 1 extra unit, we go up to close to 99, and then we reach our target goal of 99.9% reliability by adding 2 extra turbines. Medium speed engines, we need to add 4 or 5 engines to hit that 99.9% reliability. As I mentioned already, with our 2.5 megawatt units, we're having to add quite a few extra engines of 15 engines. But here's the important point. If our base build is 250, we've only deployed an extra 40 megawatts versus almost an extra 100 megawatts. That results in an overbuild reduction of as much as 18% to achieve a similar reliability. This means that we can reduce our overall CapEx. And again, I want to thank Robert McEnroth for helping develop these capital estimates, where we can save as much as $100 million in power deployment to satisfy that reliability requirement. So one of the benefits of going smaller is being able to achieve a higher reliability with less power deployed and less CapEx.